Hello, my name is Tyler, and it is my pleasure to present you with NoFib, our group senior design project. Atrial fibrillation is the most common arrhythmia amongst middle-aged athletes, ages 30 to 50. It is an irregular and often rapid heart rate that occurs when the two upper chambers of your heart experience chaotic electrical signals. If it goes undiagnosed, several severe issues can occur in due time, such as stroke and cardiac infarctions, better known as heart attacks. Per our research, if these chaotic events that result can be tended to within 15 minutes, the chances of survival increase by 90%. A current problem with the pandemic is athletes cannot get an appointment to go see their cardiologist or physical therapist, or are simply not comfortable going to the clinic. However, they still wish to track their cardiac recovery. This creates an issue in the current landscape. Even athletes who do not have a history of cardiac deficits are still being forced to work at home due to widespread gym closures or simply them not being comfortable. CNN Business reported an all-time high sale of home workout equipment like Peloton. Sometimes percent increases can be non-intentionally misleading, but an increase in 167% corresponds to 2.67 times the normal amount of Pelotons being bought in this period. Middle-aged populations were also reported to be the least likely population to return to the gym after the pandemic. BBC WorkLife reports 59% of people ages 30 to 50 do not plan on renewing their gym memberships. There are two main incentives for creating our device. One is the prevalence of atrial fibrillation in normal times, and two is this pandemic switching a lot of workouts to being in the home, especially for the middle-aged population, which is most vulnerable to this arrhythmia. Our goal is to build a low-cost heart monitoring device that can detect heart arrhythmias in real time and rapidly notify an emergency contact to address the unprecedented need for at-home cardiac monitoring. We did this with filtering algorithms, machine learning, specifically a deep learning model, and by creating a wearable with built-in ECG leads to lower stigmatization.
Alright, so there are currently a few devices on the market which have similar functionality to that of our NoFib device, one of which is an Apple Watch, which does not actually require an ECG tracing, but interprets an ECG signal from various factors, including heart rate and blood pressure, and this ultimately limits arrhythmia detection solely to AFib. Another one of which is a Holter monitor, which research shows that are very stigmatizing and are often very bulking, resulting in patients not wanting to wear it around in public or for large amounts of time. Additionally, neither of these devices have direct interventional benefit on the patient. Another one of these devices is a pacemaker, which requires surgical implementation and costs ample amounts of money, which deters patients from getting this device in the first place to help and treat their condition. So here's a video of our device in action. As you can see, the box storing the circuitry of our device is secure in the back pocket of Campbell's shirts, with the electrodes feeding through the back of the shirts through channels in the shirt onto Campbell's chest for easy replaceability of the electrodes. So as you can see, Campbell is exercising. Here I'm connecting to the port which is reading in the serial data, and as you can see, an ECG signal is being displayed on the screen, and after about 1 second, as you can see, the outcome switches from unknown to healthy. So this is an abnormal AFib ECG tracing from an online database, and as you can see, the outcome monitor correctly displays abnormal.
So for the next couple minutes or so, I'm going to be talking about the hardware setup and function of this project. So the first part of using our device that would happen would be taking any ECG electrodes, placing them on the chest in the proper spots, then placing the shirt on, and the shirt has little cloth channels sewn into it where the leads would be, so that when you put the shirt on, the leads are already sitting over top of the electrodes. You can just snap them into place, and you won't get a lot of movement from the wire to the electrode. Next is the heart rate monitor. This is what is attached to the EKG leads and is picking up that data. This data is then fed to a microcontroller, which for the first one, it's in Arduino Uno. This is being powered by an external power source and a 9-volt battery, which are both housed on the lid and the casing of the device. All of the data that's collected by the heart rate monitor and fed into the Arduino will then be pushed through our first Bluetooth module to our second receiving Bluetooth module, which is subsequently connected to another microcontroller. All of that data that is collected from the portable side of our device is sent to this side of the device, it's hooked up to a computer, and then it can be pushed into our program and our algorithm to be interpreted. So our main goal for the hardware setup is to have a total process that's quick, that's effective, that's cheap, and is uninhibiting to the athlete during a workout.
We'll start with the front end of our application, which is based on Java. We first enter our Twilio information, which allows us to send the SMS message to the caregiver, and then we leverage JChart to open up a user-friendly GUI, which can display the ECG signal. That serial information is then fed into our Python backend, which is a deep neural network that Ben can talk about more, and that is how we get our prediction of healthy or abnormal.
So for the specifications on the machine learning side of things, we wanted an accuracy above 95%, which we were not able to achieve, but we were pretty close. We also feel pretty good about our false positive and false negative rates. As you can see, we decided that the false negative rate should be more stringent because it's way worse to not detect somebody that's actually undergoing a possibly life-threatening arrhythmia. As well, our rate of detection speed was achieved. We were hoping for less than 2 seconds, and we're able to achieve 1 second of detection time. As well, we wanted an SMS send time of 5 seconds, but we're ultimately limited by the connection speed of our Wi-Fi as well as the Twilio server.
The NoFib device uses a recurrent neural network, which is a model based on real neurons and how they are able to learn. The neural network is able to make predictions from an ECG signal and classify it as either healthy or atrial fibrillation. It is able to do so using features that are extracted using both our dense layers and our LSTM layer. The dense layers, as pictured in the top right, are able to interpret the features and classify them into outputs. The features are extracted using the long short-term memory, or LSTM layer, which is able to detect patterns in time series data, such as the ECG signal pictured in the bottom right, and turn that into the features we want. Through the use of a high-pass and a low-pass filter, we found that our NoFib device can produce consistent and reproducible ECG signals across patients. Not only is our machine learning algorithm over 90% accurate, but it could easily be tweaked to be applied to other different kinds of arrhythmias, such as VFib and VTAC. In conclusion, NoFib is a proof of concept for at-home monitoring of arrhythmias for at-risk athletes with a user-friendly UI.
So as Campbell had said earlier, originally we were planning on having our device cost around $250, but after numerous changes to our design and simplifying the circuitry, we were able to make it cost $116 using the most cost-effective parts we had available. And it also goes to show that if needed, we could use more powerful and more expensive parts to replace what we have in order to expand the functionality and range of uses for our device. And so leading on from that into our future steps, we want to be able to have some better stress testing because we used a seated bike, which doesn't create too much noise because there's not that much movement in the upper body. But we want to try to include some filters to help allow the signal to be clear when doing exercises like running or the elliptical. We also want to look at overfitting and try to reduce the overfitting that we have in our machine learning model by doing clinical trials, and then also maybe add some more leads as recommended by our mentor, Dr. Douglas Jacoby, to get a clear signal. And then doing so, we want to be able to address more arrhythmias and better compete with companies like Apple and their devices like the smartwatch.